Today's aim, Kipsters will be able to solve scale and unit conversion problems using dimensional analysis. So you see that I've introduced two more types of problems today. We've been working on basic rate problems. We've introduced two different types of problems today, scale and unit conversion problems, but you're seeing that we're also going to be using dimensional analysis for this. So this should be like, wow, Mr. Boots, dimensional analysis is so powerful. This is already the third type of problem that we're able to use this same basic idea of dimensional analysis to set up and solve. Thank you, Mr. Boots, for teaching me dimensional analysis. You're so awesome. I could read your thoughts. I could read your thoughts. All right.
No, you can't remind.
23. Gotcha. All right. So you'll see that I've already written up your key points for today. That was to help make things move a little bit more swiftly. And we're going to read that unit conversion problems are just rates in hiding, and a scale factor is just a rate. So it sounds like the reason we're using dimensional analysis is because we can treat these problems just like rate problems. So the first problem that we run into is a scale problem. Back in the Stone Ages, before everybody had GPS in their cars and on their phones and all that good stuff, and you actually had to figure out where you were going by looking at a map. Are you guys familiar with maps? Have you guys seen a map before? Okay. You had to determine, how far it was away from something by using the scale on the map. So the scale is right up here on the top of the map. And it's telling me that this distance that I can measure, looks kind of like a centimeter on my screen, is equal to 600 feet. So we're just going to call that 1 unit, because I don't really know how long it really is. 1 unit is equal to 600 feet. And so here we are. This looks a lot like a rate because it's a relationship between two different types of units. So this is kind of like, we could read this as we have 1 unit for every 600 feet, or for every 600 feet in the real world, we've used this 1 unit to measure it. So I can measure the distance from school to Alamo Square Park, and I can kind of use these units, and I'm just going to freehand it here. That's about a unit. That's about a unit. So it's about 1, 2, 3, 4 units. So my distance from here to here is about 4 units. But obviously, this doesn't give us a whole lot of good information for the real world because, hey, I'm 4 units away. All right, so what's a unit? 4 steps. 1, 2, 3, 4. Hey, I'm at Alamo Square Park. I'm 4 units away, right? No, so we got to figure out what that really means. So we can use the scale to help determine what that really means. This is our rate right here. So when we go down to set up this problem, our given rate is just that scale factor. For every 1 unit, it is 600 feet. Oh, 600 feet. Or, for every 600 feet, I'm writing this down. For every 600 feet,
Okay, I gotta concentrate.
it is 1 unit on the map. All right? So the situation, that's what we're trying to measure. On the map, how many units away is Alamo Square Park from school?
5 blocks.
How did I measure? I had to measure in the units. How many units? 4. 4 units. So our situation is just 4 units. And so our answer here is
Number 2.
we want to find out Alamo Square Park, or ASP, is blank feet away. So, here we are. Oh, type of problem. Boom. Good idea. What type of problem is this? It's a lot like a basic rate, but we're going to give it the very specific name because it is a very specific type of problem. This is a scale problem. We find scales in lots of different places. We find scales on maps, and sometimes architects, engineers use lots of scales when they're drawing or trying to represent the things that they're trying to design. So this type of problem is a scale problem. But as we look back up at that key point, we can see that a scale factor is just a rate. So this is really just treated like a rate problem. We start with the units of our answer. Over here is feet. And show me number 1 or number 2. Which of these two rates or scale factors am I going to be using? Looking around, looking around, looking around. Which of these two am I going to be using? Okay, you guys are telling me that I need to match up my feet with my feet. 600 feet for my 1 unit. That matches up my feet across from my feet, just the way we like it. And now I've got these extra units that I need to get rid of. That's where we're going to plug in our situation right here for units. And we're just going to double check by canceling out our units. Units cancel out with units. Leslie? Top times top is
600 times 4. You supposed to put the answer there?
Make sure you keep all those zeros. All right, so we get that it is 2,400 feet away. All right, we get that it is 2,400 feet away. When we think about walking distances, though, how many of you, when you think about walking distances, long distances like this, do you think, all right, from here to my house, it is 24,326 feet? None of us actually think about it like that. So instead, we tend to think about that in terms of miles. So this actually creates a different type of problem for us. We know how far it is in feet. So this is kind of like this problem would start with, we know it is 2,400 feet to Alamo Square Park, ASP. And since we know the distance in feet, when we want to walk somewhere, generally we want to think about it in miles. So feet and miles both measure the same type of thing, which is distance. They're just two different measures. Just like when we talk about money, you know, some places talk about money in terms of dollars. Some of them talk about it in terms of euros. Sometimes when you go some places, they talk about distance in meters, feet, yards. All of these different things, it's all within the same type of measurement. They're just different units. So this is what we call a unit conversion problem. So you're going to come down here, you're going to write your type problem. This is a unit conversion problem. This is a unit conversion problem. We're still measuring distance. We just need different measures of distance that we want to use. So the rate here is just our conversion factor. How many feet to how many miles? There's a very excellent resource, not that I'm going to have you look it up today, but on page 8 of your agenda, in case you ever run into a unit conversion problem. If you have your agenda on your desk, you're welcome to look. I don't want to dump her stuff all over the place. On the, here, you babysit that. Let go away. Don't touch it. All right, so up here and up here where you see my fingers, they have a bunch of different unit conversions. So this is where you can find unit conversions if you don't know them. However, what we'll find in here is that it will tell us that 1 mile is equal to 5,280 feet. So, if we think about this, all right, I apologize that I gave you instructions to look in your agenda for this conversion factor, and I know that you're super excited. Oh my gosh, look at this awesome resource that we have. But let's make sure that we bring it back because we're ready to do this problem. Okay, so we have 1 mile is equal to 5,280 feet. Okay, so if I want to write that as a rate, the way that we've been writing rates, how do you think I would write that? If I wanted to write that as a rate, how do you think I would write that, Viviana?
You should erase that.
Yeah, 5,280 feet. And so those unit conversion factors are really just rates. I could write this the other way. 5,280 feet over 1 mile. So for me, when I was in middle school, actually, and to this day, I have lots of problems with unit conversions. I'm like, all right, wait, it's 3 feet to a yard. I need to find it out in yards. Do I need to multiply or do I need to divide?
Divide.
Oh, it's really confusing for me. So I always actually set up these unit conversions just like rate problems, and that's how I know. How do I know how to multiply and how do I know to divide? And this is kind of one of the key ideas in this particular unit is that the units can tell you exactly what you need to do. So our answer is we want to know it is blank miles to Alma Square Park. And our situation up here is 2,400. I don't have space for that, so I'm just going to label it up here, situation. And so this is, for me, this is how I set up. When I have problems like this, even today, when I was in physics, when I was in college, when I was in middle school and I was your age, this is how I would figure out. Do I need a multiplier? Do I need a divide? I would say, all right, it's just a dimensional analysis. I need my answer in miles. I need to match that up, so I have 1 mile over 5,280 feet. And I get 2,400 feet and feet. So the way that I knew what to do here was I would make sure that the units canceled out. And this tells us that in this problem, we end up doing division. 2,400 over 5,280. Okay. I'm not going to do this division right now because it would take us a little bit of time that we don't necessarily have. I know that this comes out to approximately, if I rounded it to the nearest tenth, approximately 0.2 something. Right? 0.2 something. So, but the important part is that we know how to get there. Any questions about this unit conversion problem? Kevin? Dimensional analysis. Oh, GPS. Does a GPS do all of this for you?
Yes.
Yeah? Shh. That's not the point. So the point is that you run into these things a lot, not necessarily feet and miles, not necessarily scale factors, things like that.
So
the scale factors, I think, are going to be more important for those of you who want to go into science as a field. Anytime you have drawings of things, architects, anything like that, or people even do landscaping. When you're talking about planning things that are house-sized and you want to plan them on paper, you end up using scales. Artists actually use scales a lot as well. Okay, Leslie. Yeah, so in this case, we could use two-dimensional analysis problems to go from map to how many miles it is to Alamo Square Park. All right? So let's look at another unit conversion problem. It tells you that the paper that you are working on is 8.5 inches wide. It says how wide is it in centimeters. So, as I'm sure most of you are well aware, Judea, because you've probably been taught this in science at some point. The rest of the world uses metric units. We're pretty much the only country in the world that is stuck on inches and feet. Okay? Pretty much everybody else has figured out, hey, guess what? Meters is way easier. But hey, one day we'll figure that out. Until we figure that out, a lot of times when we want to talk to our friends from, Europe, Australia, wherever, they're going to measure things in terms of these metric units. So when they talk about the width of a paper, they're probably going to talk about it in terms of centimeters. So unfortunately, in the United States, we've put ourselves in the position where we have to do a lot of these types of unit conversions. So our unit conversion tells us that 1 inch is equal to 2.5 centimeters. If we're going to solve this like it is a rate problem, that means that 1 inch over 2.5 centimeters is our rate. So conversion factors are just rates. They're hiding. 2.5 centimeters is 1 inch. Now, the situation we're talking about here is the width of our paper. So our situation is 8.5 inches. And if we're looking at our question, it says, how wide is it in centimeters? It is blank centimeters wide. This type of problem is a unit conversion. All right, so if I want to set this up, I always start with the units of our answer. All right, somebody filled in the blank. Everybody else? Answer. Okay, we always start with the units of our answer. We see our units should be centimeters. Which of the two rates do I want to use? Number 1 or number 2? Door number 1 or door number 2?
2.
See some of you catching up in the writing.
One.
Thank you for showing me with your fingers.
What?
Door number 1 or door number 2? Rate number 1 or rate number 2? Which of these do I want to match up? 4 is not an answer. All right, looking at 2.5 centimeters over 1 inch. So now we've got these extra units of inches that we need to get rid of. 8.5 inches, that's our situation. Inches cancel out. This tells us in this case, this is a problem where we need to multiply. So we get 8.5 times 2.5. That one we can actually do pretty quickly. So let's go ahead and finish up this problem. 8.5 times 2.5. 5, carry the 2 is 42, 0, 0, carry the 1, 2 times 8 is 16, 17, so 5, 2, 1, carry the 1, 20, 2,125, nope, decimal 1, 2 times 21.25 centimeters.
A pencil. Anybody has lead.
So looking at this next problem, it says my car weighs 2.2 tons. How many kilograms does my car weigh? Okay, so this really starts really easy. Our answer is how many kilograms does my car weigh? So our answer is it weighs blank kilograms. Okay, so that part's easy. I know my situation is that my car weighs 2.2 tons. And so as I'm getting ready to set up this dimensional analysis, I know that I need my answer to be in kilograms. The unfortunate thing, though, is if I start looking in the back of my agenda, it doesn't give me a rate for kilograms to tons. So when I'm looking for my relationship with tons, the only thing it tells me is that 1 ton is equal to 2,000 pounds. Well, that doesn't get me all the way, because if I try and plug that in, I'm never going to end up with kilograms on top. So as I'm looking through, I can find that 1 kilogram is equal to 2.2 pounds. All right, so that helps. I can use that. I can get 1 kilogram over 2.2 pounds. That's awesome. Look, I got my units matched up. I got a kilogram right across from a kilogram. That's what I want. That's what dimensional analysis says.
Yep.
All right? The problem is, look what happens when I plug in my situation. 2.2 tons. What happens with my units? Alvaro? Yeah, they're different. These can't cancel out. I can't cancel out tons with pounds. So what I can do, Kyrie, what do you think?
You can turn 2.2 tons into, well, you can change it into pounds.
So he's saying change my tons into pounds.
Pounds.
So, well, how do I do that? I can actually just throw that right into my dimensional analysis. And I could say, all right, I need these tons to cancel out. So 1 ton over 2,000, and I'm sorry that's so messy, pounds. Now, pounds over here now cancels out with pounds over here. Kilograms over here now cancels out with, oh wait, I don't want kilograms to cancel out. That's what I want my answer to be. No, don't go away. All right, this is kilograms, still here, because it didn't cancel out with anything. But my tons now cancel out with the tons over here. So when I look through, the only units I have left were these kilograms. That's what dimensional analysis does. It says, hey, you don't have to know how to convert between this and that, and then this and that. You can just set it up and let the units guide the way. So what we would end up doing on this was we would multiply 2,000 times 2.2 tons. We get 4,400. And on the bottom, we'd end up with 2.2. This is this one? This one? That's 1 kilogram. Okay. So we're going to spend a lot more time on problems like this later on in the unit. But I wanted to go ahead and expose you to these type of problems because some of you are ready to push yourself here. And for the rest of you who aren't quite ready to push yourself here, I want you to know this is the reason why dimensional analysis is so powerful. Is you can take problems like this where you would used to have to do like 8 different proportions to solve it, and you can just do it all in one multiplication and division, okay? And the units will tell you exactly what you need to do, all right? So with that in mind,